Hello there, and welcome to this gentle journey through the cosmos, where we'll drift slowly toward the edge of time itself. Tonight we're going to explore one of the most profound questions in all of science. What happens at the very beginning and end of the universe? It's a question that carries us from the first moments after the Big Bang to the distant future when the last stars will fade into darkness. We'll move at the pace of a quiet breath, letting each idea settle softly in your mind before moving to the next, allowing the vastness of cosmic time to wash over us like gentle waves. Before we begin, take a moment to settle in wherever you are. Perhaps you're lying in bed with the lights dimmed, feeling the softness of your pillow beneath your head. Maybe you're in a comfortable chair, looking for a moment of calm after a long day. Or perhaps you're somewhere peaceful, watching the evening sky deepen into night. Either way, you and I are about to share something remarkable. A journey across not just space, but time itself, from the very first tick of the cosmic clock to its final fading chime. If you find this kind of gentle exploration soothing, feel free to let others know so they too can find this quiet voice when they need it most. Now take a deep breath and let your mind relax completely. Feel your shoulders dropping, your jaw unclenching, your breathing becoming slower and more natural. Tonight we're going to travel from the very first fraction of a second of the universe's existence, all the way to its final moments, trillions upon trillions, trillions of years in the future. It's a journey that will take us through cosmic epochs so vast that all of human history becomes just a fleeting moment, like a single heartbeat in a lifetime. And yet somehow we can trace this entire timeline from where we sit right now, in this quiet moment, surrounded by atoms that are older than the Earth itself. Imagine for a moment that you could step outside of time itself and look at the universe's entire history laid out before you, like a vast rolling landscape stretching to every horizon. At one end, you'd see the brilliant flash of the Big Bang, so energetic and dense that matter as we know it couldn't even exist. The temperature would be beyond anything we can truly comprehend, hotter than the center of the most massive stars, hotter than anything that exists in the universe today. At the other end of this temporal landscape, you'd see a cold, dark cosmos where the last remnants of matter have decayed into the simplest particles, drifting through a space so vast and empty that the distances between particles are measured not in light years, but in scales that dwarf entire galaxy clusters. This is the timeline we'll explore together tonight, not rushing through it like a textbook, but allowing each era to unfold in our imagination like a slow cosmic meditation. The journey begins not with a place, but with a moment so brief and so intense that it defies easy description. The Big Bang wasn't an explosion in space, as it's sometimes depicted in movies or illustrations. Rather, it was an explosion of space itself, an expansion of the very fabric of reality. About 13.8 billion years ago, everything we can observe today, every galaxy spinning through the cosmos, every star burning in the night, every planet orbiting its sun, every atom in your body, every thought in your mind was concentrated in a region smaller than the period at the end of this sentence. Try to picture that for a moment. Everything that exists, compressed into a space so tiny that it makes a grain of sand look vast by comparison. The temperature at this moment was so high, the density so extreme, that our normal concepts of matter and energy break down completely. This wasn't just hot in the way we understand heat, like the surface of the sun or the flame of a candle. It was so energetic that particles and antiparticles appeared and disappeared in fractions of seconds, matter and antimatter annihilating each other in flashes of pure energy, while the fundamental forces that govern our world today, gravity, electromagnetism, the strong and weak nuclear forces, were unified into something we can barely comprehend, a single primordial force that contained within it all the complexity that would later unfold. In the first unimaginably brief fraction of a second after the Big Bang, something extraordinary happened that cosmologists call cosmic inflation. Space itself expanded faster than the speed of light, stretching tiny quantum fluctuations, variations so small they existed only in the realm of uncertainty and probability, into variations in density that would eventually become the seeds of galaxies, the foundations upon which all future structure would be built. This inflation lasted less than a second, a time span so brief that light couldn't even travel across an atom during its duration, but in that almost infinitely short moment, the universe grew from subatomic scales to something larger than a grapefruit, then larger than a building, then larger than a planet. It's almost impossible to picture this kind of expansion, but imagine watching a balloon being inflated, except instead of taking several seconds to grow from tiny to large, it happens in a time so short that if you blinked, you would miss billions upon billions of doublings in size. And this wasn't just a balloon expanding into empty air, but space itself stretching, creating new regions of reality where none had existed before, carrying with it the seeds of everything that would eventually become stars, planets, and life itself. During this inflation, the observable universe today, with all its billions of galaxies, grew from a region smaller than a proton to something much larger than what we can see with our most powerful telescopes. As the universe continued to expand and cool following this brief but dramatic inflationary period, it entered what physicists call the Radiation Era, a time when the cosmos was dominated not by matter as we know it, but by pure energy in the form of radiation. For the first few minutes after the Big Bang, the universe remained far too hot for atoms to form and stay together. Instead, it was a seething soup of fundamental particles, protons and neutrons, the building blocks of atomic nuclei, electrons with their negative charge, and photons carrying electromagnetic energy, all colliding and interacting in a cosmic dance of pure energy that filled every corner of space. The temperature during this time was measured not in thousands or millions of degrees, but in billions of degrees, hot enough that even the nuclei of atoms couldn't remain bound together in anything but the simplest forms. But as the universe expanded, this incredible heat began to dissipate, spread thinner across an ever-growing volume of space. And during these first few crucial minutes of cosmic history, something remarkable happened that would determine the chemical composition of the universe for billions of years to come. The first atomic nuclei formed through a process called Big Bang Nucleosynthesis. Picture this ancient cosmic kitchen where the universe itself was a crucible hot enough to forge the very elements that would one day become planets and people. In those first minutes, as the temperature dropped from billions to hundreds of millions of degrees, protons and neutrons began to stick together, forming the nuclei of the lightest elements. Hydrogen nuclei, consisting of single protons, were already present, but now helium nuclei began to form, each consisting of 2 protons and 2 neutrons bound together by the strong nuclear force. Small amounts of lithium and beryllium nuclei also formed, but the universe was cooling and expanding so rapidly that this primordial element formation lasted only a few minutes before conditions became too cool for further nuclear reactions. This brief period of nucleosynthesis determined that about 3/4 of all normal matter in the universe would be hydrogen, the simplest and most abundant element, while most of the remaining quarter would be helium. These proportions remain essentially unchanged today, billions of years later. When we look at the most distant galaxies, formed when the universe was young, or when we analyze the composition of the oldest stars, we still see this ancient signature of the Big Bang, this cosmic recipe written in the first few minutes of time. For the next 380,000 years, a span of time longer than all of recorded human history, the universe remained in a state that would be completely alien to us today. It was opaque, filled with a hot plasma where electrons moved freely among the nuclei, and light couldn't travel far before hitting a free electron and being scattered in a random direction. Imagine trying to see through a thick fog, except this fog filled all of space, from one edge of the universe to the other. The cosmic fog wasn't made of water droplets, but of free electrons that scattered photons endlessly, making the universe as opaque as the interior of a star. But as the universe continued its relentless expansion, growing larger and cooler with each passing millennium, something beautiful and transformative slowly began to happen. The temperature dropped gradually but steadily, and after those 380,000 years of cosmic fog, it finally became cool enough for electrons to combine with nuclei to form the first complete atoms. This moment, which cosmologists call recombination, cleared the cosmic fog and allowed light to travel freely through space for the first time since the universe's birth. Picture this moment not as a sudden switch being flipped, but as a gradual dawn breaking across the entire universe. For thousands of years, the fog slowly thinned as more and more electrons found their way into atomic orbits, bound to nuclei by electromagnetic attraction. The universe gradually became transparent, and the light that had been trapped and scattered for hundreds of thousands of years was suddenly free to travel unimpeded across cosmic distances. This is the light we still detect today as the cosmic microwave background radiation, the afterglow of the Big Bang itself, stretched and cooled by billions of years of cosmic expansion until it appears not as visible light, but as faint microwaves that fill every cubic centimetre of space. If you could have been present during recombination, floating somehow in this primordial cosmos, you would have witnessed one of the most significant transitions in cosmic history. The last glowing embers of the Big Bang gradually faded as atoms formed and space became clear and dark for the first time. The universe was entering a new phase, no longer dominated by radiation, but by matter, by the hydrogen and helium atoms that would eventually collapse under their own gravity to form the first stars and galaxies. This transition marked the beginning of what cosmologists call the Dark Age, a period lasting tens of millions of years when no stars had yet formed and the universe was lit only by the fading afterglow of creation. It was dark not because there was no matter, but because there were no sources of light. The hydrogen and helium atoms drifted through space in vast invisible clouds, cooling slowly as the universe expanded around them. To our eyes, this cosmic dark age would have appeared completely black, but it was pregnant with potential, filled with the raw materials that gravity would eventually sculpt into the first cosmic structures. During this dark age, which lasted much longer than the entire history of complex life on Earth, gravity began its slow but absolutely relentless work of cosmic architecture. Those tiny density fluctuations created during the inflationary epoch, variations in density so small they were originally just quantum uncertainties, began to grow under the influence of gravitational attraction. Regions that were even slightly denser than average started to pull in more matter from their surroundings, while less dense regions gradually emptied out as their matter was drawn toward these growing concentration points. This process unfolded over tens of millions of years, with gravity acting like an invisible sculptor, shaping the smooth, nearly uniform cosmos left over from the Big Bang into an intricate web of structure. The densest regions became the cores around which the first galaxies would eventually form, while the less dense regions became the vast cosmic voids that separate galaxy clusters today. Over millions of years, these fluctuations grew into the cosmic web we observe today, a vast three-dimensional network of dark matter filaments along which ordinary matter would eventually flow like water, following the contours of an invisible landscape. The end of the Dark Age came with one of the most beautiful and significant events in all of cosmic history, the birth of the first stars. About 200 million years after the Big Bang, when the universe was still less than 1/50th of its current age, gravity had finally managed to pull together enough hydrogen and helium in the densest regions of dark matter halos to overcome the outward pressure of gas and trigger the collapse that leads to stellar ignition. These first stars were very different from our Sun and the stars we see today. They were giants, perhaps 50 to 100 times more massive than our Sun, burning with an intensity that made them incredibly luminous, but also incredibly short-lived. Picture these first stellar fires flickering to life in the cosmic darkness, like candles being lit one by one across a vast cathedral. Each new star was a nuclear furnace, converting hydrogen into helium in its core through the process of nuclear fusion, the same process that powers our Sun, but operating on a much more dramatic scale. These massive first-generation stars burned brilliantly but briefly, living fast and dying young in spectacular supernova explosions that could outshine entire galaxies for months at a time. When they died, they scattered the first heavy elements, carbon and oxygen, silicon and iron, magnesium and neon, into the surrounding space like cosmic seeds. This was the moment when the universe first began to shine again after the long dark age, ending hundreds of millions of years of darkness with the light of stellar fire. But these stars did more than just provide light. They were cosmic alchemists, transforming the simple hydrogen and helium of the early universe into the complex elements that would make planets and eventually life possible. In their cores, under temperatures of hundreds of millions of degrees and pressures, billions of times greater than Earth's atmosphere, nuclear fusion reactions built up heavier and heavier elements from the light nuclei created in the Big Bang. Carbon formed when 3 helium nuclei combined in a process that requires precise timing and conditions. Oxygen formed when carbon nuclei captured additional helium nuclei. Silicon, magnesium, neon, and sulfur formed through further nuclear reactions. And in the final moments of these massive stars' lives, as their cores collapsed and then exploded outward in supernova blasts, the incredible temperatures and pressures created elements even heavier than iron, cobalt and nickel, zinc and copper, and trace amounts of gold, silver, and other precious metals. When these first stars died in their supernova explosions, they seeded the universe with these heavy elements for the first time. The shock waves from their explosions swept through the surrounding hydrogen and helium clouds, compressing them and triggering the formation of new stars. These second-generation stars formed from material that was no longer purely hydrogen and helium, but contained small amounts of heavier elements, the ashes of their stellar predecessors. This marked a crucial transition. For the first time, it became possible for rocky planets to form around stars, because rocky planets require elements heavier than hydrogen and helium. The process of stellar death and rebirth continued for millions of years, with each generation of stars adding more heavy elements to the cosmic mix. With each cycle, the universe became more chemically complex, more interesting, more capable of supporting the kind of intricate chemistry that life requires. Oxygen, so essential for the water that fills our oceans and the respiration that powers our cells. Carbon, the backbone of all organic molecules. Iron, which flows through our bloodstream and enables our blood to carry oxygen. Calcium, which strengthens our bones and enables our neurons to communicate. All of these elements were forged in the nuclear fires of ancient stars that lived and died long before our solar system was even a distant possibility. In a very real and literal sense, we are made of star stuff, as astronomer Carl Sagan so eloquently put it. Every atom in your body, except for the hydrogen, was forged in the core of a star that existed billions of years ago. The calcium in your teeth was created when a massive star fused silicon nuclei together in its final moments. The iron in your blood was forged in the last seconds before a supernova explosion. The oxygen you're breathing right now was created when helium nuclei collided with carbon in the heart of a dying star. We are not just observers of the cosmos, we are participants in it, made from it, inseparable from the long chain of cosmic evolution that stretches back to the Big Bang itself. As more and more generations of stars lived and died, enriching space with heavy elements, they began to gather into larger and larger structures under the influence of gravity. The first galaxies were smaller and more chaotic than the elegant spirals and ellipticals we see today, often merging and colliding as gravity pulled them together in a cosmic dance of construction. These early galaxies were like stellar nurseries, places where gas clouds could collapse more easily and form stars more rapidly than in the emptier regions of space. But with each merger, with each generation of stars, with each cycle of stellar birth and death, the universe became more structured, more organized, more complex. Galaxy clusters formed as gravity pulled individual galaxies together into vast groups containing hundreds or thousands of members. The cosmic web became more pronounced, with matter flowing along dark matter filaments like rivers following the contours of a landscape, creating the large-scale structure we observe in today's universe. Clusters connected by filaments, separated by vast voids that contain relatively few galaxies. This process of structure formation unfolded over billions of years, with gravity acting as the architect and stars as the builders, slowly assembling the raw materials of the Big Bang into the magnificent cosmic structures we observe today. The universe evolved from simplicity to complexity, from near uniformity to intricate organization, from a smooth sea of particles to a cosmic web of galaxies, clusters, and superclusters spanning billions of light years. About 9 billion years after the Big Bang, when the universe had reached about 2/3 of its current age, something particularly significant happened in a quiet region of a spiral galaxy we now call the Milky Way. A cloud of gas and dust, enriched by several generations of stellar nucleosynthesis and containing all the elements necessary for rocky planet formation, began to collapse under its own gravitational attraction. This collapse was probably triggered by the shock wave from a nearby supernova explosion, which compressed the cloud just enough to overcome the outward pressure of gas and begin the process of gravitational contraction. Over the course of several million years, this cloud continued to collapse and fragment, with most of the mass falling toward the center, where it would eventually become dense and hot enough to ignite nuclear fusion and become our sun. Meanwhile, in the flattened disk of remaining materials surrounding the young star, solid particles began to stick together, forming larger and larger aggregates through a process of accretion. Close to the star, where temperatures were high, only rocky and metallic materials could condense, forming the ingredients for terrestrial planets like Mercury, Venus, Earth, and Mars. Further out, where temperatures were cooler, water ice and other frozen compounds could survive, providing the material for the gas giant planets like Jupiter and Saturn. Earth formed as one of these rocky worlds about 4.5 billion years ago, when the universe was already about 9.3 billion years old. Initially, our planet was a hellish place, bombarded by asteroids and comets in a period called the Late Heavy Bombardment, its surface covered by oceans of molten rock. The early atmosphere contained virtually no oxygen, instead consisting mainly of carbon dioxide, water vapor, methane, and other gases. The young Earth was nothing like the blue marble we know today, with its oxygen-rich atmosphere, vast oceans, and abundant life. But slowly, over hundreds of millions of years, our planet began to transform. Water vapor in the atmosphere condensed into rainfall that lasted for centuries, filling the first oceans as the surface gradually cooled. Volcanic activity released gases from the interior, helping to build up an atmosphere, though one that would have been toxic to most life as we know it today. And somewhere in those early oceans, perhaps in the vicinity of underwater volcanic vents, or perhaps in tidal pools warmed by the young sun, the first primitive life forms emerged. Life on Earth appeared surprisingly quickly after the planet became habitable, with evidence of simple microorganisms appearing in rocks as old as 3.8 billion years. For most of Earth's history, life remained simple. Single-celled organisms that slowly but profoundly transformed the planet's atmosphere by producing oxygen as a waste product of photosynthesis. This oxygen was initially toxic to most life forms, causing what some scientists call the Great Oxidation Event about 2.4 billion years ago, which was actually a mass extinction that wiped out many of the early anaerobic organisms. But this oxygen catastrophe, as devastating as it was for early life, set the stage for more complex forms of life that could use oxygen for respiration, enabling much more efficient metabolism and eventually making possible the evolution of complex multicellular organisms. For billions of years, however, life remained mostly microscopic. It wasn't until about 600 million years ago that the first large, complex, multicellular organisms appeared in the fossil record, and not until about 540 million years ago that complex life exploded in diversity during what paleontologists call the Cambrian explosion. From that point on, Earth's story became increasingly rich and complex. Creatures with shells and skeletons left abundant fossils that tell the story of evolution, the rise of fish in the oceans, the colonization of land by plants and then animals, the age of amphibians, the rise of reptiles, and eventually the long reign of dinosaurs that lasted for over 150 million years. Dinosaurs ruled the Earth for a period longer than the entire history of mammals, until a catastrophic asteroid impact 66 million years ago cleared the way for mammals to diversify and eventually give rise to primates, and eventually to our own species. Our species, Homo sapiens, has existed for only about 300,000 years, which is truly just a blink of an eye in cosmic terms. If the entire history of the universe were compressed into a single year, with the Big Bang occurring on January 1st, then our species would have appeared only in the last few minutes before midnight on December 31st. Human civilization, with the development of agriculture, writing, and cities, has existed for only about 10,000 years, which would be just the last few seconds of that cosmic year. And yet, in this incredibly brief moment of cosmic time, we've developed the remarkable ability to understand our place in the universe's vast timeline. We've learned to trace our origins back through billions of years to the Big Bang itself, to understand that we're made of elements forged in stellar cores, to measure the age and size of the universe, and to peer both backward into cosmic history and forward into the universe's distant future. In the few thousand years since we developed writing, we've gone from thinking the Earth was the center of everything to understanding that we're one planet among billions, orbiting an ordinary star in a typical galaxy that's one among trillions in an observable universe that may itself be just a tiny part of something even larger. This brings us to the present moment, about 13.8 billion years after the Big Bang, when the universe is in what cosmologists call its mature phase. Star formation continues, though at a slower rate than in the past, as the universe's supply of hydrogen gas becomes more diluted by expansion, and more of it becomes locked up in stars and stellar remnants. Our Sun, a middle-aged star, has been shining steadily for about 4.6 billion years and has roughly another 5 billion years of stable hydrogen burning ahead of it before it begins to evolve into a red giant. But as we look ahead from our present moment in cosmic time, the universe's timeline stretches out in phases that dwarf everything that has come before. We live in what cosmologists call the Stelliferous Era, the Age of Stars, which began with those first stellar fires about 200 million years after the Big Bang. This era is characterized by active star formation, stellar evolution, and the ongoing enrichment of the cosmos with heavy elements. However, this age of stars, as long as it has already lasted and as familiar as it seems to us, represents only a brief chapter in the universe's much longer story. Stars are powered by nuclear fusion, the process that converts hydrogen into helium and heavier elements in their cores. This process has a built-in limit. Stars eventually exhaust their nuclear fuel supplies. The most massive stars have already lived and died many times over, enriching the universe with heavy elements but removing themselves from the cosmic inventory of active stars. Medium-sized stars like our Sun will continue burning for billions of years, but they too will eventually exhaust their fuel and end their lives as slowly cooling white dwarf stars. The longest-lived stars are the smallest red dwarfs, stars with masses less than half that of our Sun. These stars burn their fuel so slowly and efficiently that they can continue shining for hundreds of billions, or even trillions of years. But even they will eventually run out of hydrogen to burn. As the universe continues to expand and cool, making it harder for gas clouds to collapse and form new stars, the rate of star formation will gradually decline. Existing stars will continue to age and die, while fewer and fewer new stars will be born to replace them. In about 1 trillion years, roughly 70 times longer than the current age of the universe, star formation will essentially cease. The last generation of stars will be burning through their fuel supplies with no new stars forming to replace them when they die. The Stelliferous Era, which has already lasted for over 13 billion years, will gradually give way to what cosmologists call the Degenerate Era, a period dominated not by active burning stars, but by stellar remnants, white dwarf stars, neutron stars, and black holes. But before we reach that distant future, our own solar system will undergo its own dramatic transformation. In about 5 billion years, our Sun will begin the final phase of its evolution as it exhausts the hydrogen in its core. As the core contracts and heats up, the Sun will expand dramatically, becoming a red giant star hundreds of times larger than it is today. During this phase, which will last several hundred million years, the Sun may expand so much that it engulfs the orbits of Mercury and Venus, and possibly even Earth. Even if Earth survives this red giant phase by spiraling outward as the Sun loses mass, our planet will be scorched and rendered completely uninhabitable. The oceans will boil away into space, the atmosphere will be stripped away by the solar wind, and the surface will be heated to temperatures hot enough to melt rock. Any life that still exists on Earth at that distant time will have long since perished, or, hopefully, found ways to migrate to more hospitable worlds around other stars. After spending several 100 million years as a red giant, our Sun will shed its outer layers in a series of gentle pulsations, creating a beautiful planetary nebula, an expanding shell of glowing gas illuminated by the hot core that remains behind. This core, about the size of Earth but containing most of the Sun's original mass, will become a white dwarf star, gradually cooling and fading over trillions of years. White dwarfs are incredibly dense objects, with a teaspoon of white dwarf material weighing as much as an automobile, supported against further collapse by quantum mechanical pressure rather than nuclear fusion. As we look even further into the future, the timeline becomes almost incomprehensibly vast. The Degenerate Era, dominated by these stellar remnants, may last for about 10 to the 37th power years. That's a number so large it's difficult even to write out. A 1 followed by 37 zeros. To put this in perspective, the current age of the universe is only about 10 to the 10th power years, so the degenerate era will last about 10 billion times longer than the entire stelliferous era that came before it. During this unimaginably long degenerate era, the universe will be a cold, dark place, lit only occasionally by the dim glow of cooling white dwarfs, the faint emissions from matter falling into black holes, or the brief flare of brown dwarfs colliding and momentarily reigniting fusion. The temperature of empty space will be incredibly close to absolute zero, just a tiny fraction of a degree above the coldest possible temperature. Most of the matter in the universe will be locked up in these stellar remnants, slowly cooling and fading as they radiate their heat away into the expanding cosmos. But even these long-lived remnants won't persist forever. According to our current understanding of particle physics, even protons, the building blocks of atomic nuclei, are not absolutely stable. If certain theories about the fundamental nature of matter are correct, protons will very slowly decay into lighter particles and energy. The timescale for proton decay is incredibly long, with a half-life estimated at about 10 to the 34th power years. But given enough time, even the white dwarfs and neutron stars will slowly evaporate as their constituent protons decay one by one. If proton decay occurs as predicted, then after about 10 to the 34th power years, the degenerate era will give way to what cosmologists call the black hole era. During this phase, black holes will become the dominant form of mass energy in the universe, as all other matter has slowly decayed away into elementary particles and radiation. The universe will be filled mainly with electrons, positrons, neutrinos, and photons, along with black holes of various sizes ranging from those formed by stellar collapse to the supermassive black holes that once lurked at the centers of galaxies. But even black holes, despite their reputation for consuming everything that comes near them, are not eternal. In one of the most remarkable discoveries of the 20th century physics, Stephen Hawking showed that black holes actually emit radiation and slowly evaporate over time. This Hawking radiation is incredibly faint for large black holes, but it means that given enough time, even the largest black holes will eventually evaporate completely, returning their mass energy to the universe in the form of elementary particles and radiation. The evaporation time for a black hole depends on its mass. Stellar mass black holes, formed when massive stars collapse, will evaporate in about 10 to the 67th power years. The supermassive black holes that once powered quasars and resided at the centers of galaxies, with masses billions of times that of the Sun, will take much longer to evaporate, persisting for perhaps 10 to the 100th power years. This is such an unimaginably long time that if you wrote out the number in ordinary decimal notation, it would have more digits than there are atoms in the currently observable universe. As each black hole slowly shrinks through Hawking radiation, it actually gets hotter and radiates energy at an increasing rate. The final moments of a black hole's evaporation happen very quickly compared to the slow process that preceded it, ending in a brief but intense flash of gamma rays as the last remnants of mass energy are converted back into radiation. When the last supermassive black hole finally evaporates, the universe will enter what cosmologists call the heat-death era. In this final era, the universe will contain only elementary particles, photons carrying electromagnetic energy, electrons and their antimatter partners, positrons, and neutrinos, all spread so incredibly thinly through space that the average distance between particles will be larger than the size of today's entire observable universe. The temperature everywhere will be incredibly close to absolute zero, just a tiny fraction above the coldest possible temperature, and the density of matter and energy will be so low that no complex structures will be possible. This is the heat death that the laws of thermodynamics predict for our universe. Not destruction by fire or collision, but the gradual running down of all energy differences, the slow approach to maximum entropy, until the universe reaches a state where nothing interesting can happen anymore. All the energy will still be there, but it will be spread so evenly and thinly that no work can be done, no structures can form, no complexity can arise. And yet, even in this seemingly final state of ultimate cold and emptiness, some physicists speculate that the story might not be completely over. Quantum mechanics tells us that even in empty space, virtual particles are constantly appearing and disappearing due to the uncertainty principle. Given the unimaginably vast timescales available, even incredibly improbable quantum events become virtually certain to occur eventually. Some physicists speculate that quantum fluctuations might occasionally create small regions of lower entropy, possibly even allowing for the spontaneous formation of new baby universes through quantum tunneling events. The timescales involved in such speculations are so vast, they make even the evaporation of supermassive black holes seem quick by comparison. We're talking about periods of time so long that numbers lose their meaning, so long that entire cycles of cosmic evolution, from Big Bang to heat death, could play out countless times. But these ideas push at the very limits of our understanding of physics and may forever remain beyond our ability to test or verify. Other theories suggest even more exotic possibilities for the far future. Perhaps the universe will eventually collapse back in on itself in a big crunch, the time-reversed opposite of the Big Bang. Perhaps the expansion will continue to accelerate due to dark energy until space itself is stretched so rapidly that even atoms are torn apart in a big rip. Perhaps our universe is just one bubble in an eternal inflation process that creates new universes constantly, each with its own physical laws and constants. But based on our current best understanding of cosmology, the most likely scenario is a slow fade into cold emptiness, the heat death scenario that flows naturally from our observations of an accelerating expansion driven by dark energy. It's a fate that might seem melancholy, but it's so far in the future that it's almost beyond comprehension. The time from now until heat death is longer, compared to the current age of the universe, than the current age of the universe is compared to the time it takes light to cross an atom. As we contemplate this cosmic timeline stretching from the Big Bang to heat death, what strikes me most profoundly is not the vastness of it all, though it certainly is vast beyond any human ability to truly comprehend. Rather, it's the remarkable interconnectedness and continuity that runs through the entire story. The atoms in your body were forged in stellar cores that burned billions of years ago. The oxygen you're breathing was created when massive stars ended their lives in supernova explosions that briefly outshone entire galaxies. The iron flowing through your bloodstream was created in the final moments before a stellar core collapse. In temperatures and pressures so extreme they dwarf anything that exists in the universe today. You are literally made of ancient starlight, organized by billions of years of cosmic evolution into a conscious being capable of contemplating the very timeline that created you. Your consciousness is not separate from the universe, but is the universe becoming aware of itself, a temporary arrangement of matter and energy that allows the cosmos to know and wonder about its own existence. When you look up at the night sky and feel awe at the vastness of space and time, you are participating in one of the universe's most remarkable achievements, the emergence of self-awareness from simple hydrogen and helium. This perspective brings with it a profound sense of connection and belonging. We often think of ourselves as small and insignificant compared to the cosmos, and in terms of size and duration, we certainly are tiny and brief. But significance doesn't come from size or longevity. A moment of beauty has meaning, not because it lasts forever, but because it happens at all. A gesture of kindness matters not because it changes the fate of galaxies, but because it touches another conscious being. A flash of understanding, a work of art, a discovery about the nature of reality, these have value that transcends their physical scale. In a universe that began with nothing but elementary particles and energy, the fact that those particles have organized themselves through natural processes into structures capable of love, art, music, science, and wonder is nothing short of miraculous. We are not accidents or afterthoughts in the cosmic story, but rather one of its most remarkable chapters, the part where the universe develops eyes to see itself, minds to understand itself, and hearts to feel moved by its own beauty. This knowledge can bring a deep sense of peace as you prepare for sleep. You are part of a story that began 13.8 billion years ago and will continue for trillions upon trillions of years to come. The elements in your body were forged in stellar fires that burned before the Earth existed. Your consciousness is a brief flowering of complexity in a universe that trends towards simplicity over vast timescales, a candle flame of awareness flickering in the cosmic night. The universe's timeline teaches us profound lessons about patience and perspective. Stars take millions of years to form from collapsing gas clouds, billions of years to evolve through their life cycles, and trillions of years to fade into cold remnants. Galaxies merge over hundreds of millions of years in gravitational dances so slow that entire species arise and go extinct while the cosmic partners circle each other once. The cosmic web took billions of years to develop its current intricate structure of filaments and voids. Against these timescales, the urgent worries of daily life can find their proper proportion. There is a rhythm to the cosmos that is slow, steady, unhurried, and persistent. Perhaps we can learn something from this cosmic patience, allowing our own lives to unfold with less anxiety about immediate outcomes and more trust in the long arc of time. The universe doesn't rush its processes. It allows billions of years for complexity to emerge gradually from simplicity, for consciousness to arise from matter, for beauty to flower from chaos. In our own brief lives, we might find wisdom in embracing this cosmic rhythm, understanding that meaningful change often happens slowly, that growth requires patience, that the most profound transformations unfold over time, scales longer than our immediate desires might prefer. The cosmic timeline also teaches us about cycles, renewal, and the creative power of destruction. Stars are born from the gravitational collapse of gas clouds, but those clouds exist only because previous generations of stars lived, died, and returned their processed material to space. Galaxies grow through mergers that might seem catastrophic, but ultimately create larger, more complex structures. Even supernovae, among the most violent events in the universe, are essential for creating and distributing the heavy elements that make rocky planets and biological complexity possible. Nothing in the cosmos is permanent in its current form, but this impermanence is not cause for sorrow or anxiety. Instead, it's what makes change, growth, and renewal possible. The death of massive stars enables the birth of planetary systems. The collision of galaxies triggers new waves of star formation. The gradual cooling of the universe allows increasingly complex structures to form. Endings make new beginnings not just possible, but inevitable. In our own lives, we can find comfort in this cosmic principle, that endings and losses, difficult as they may be, create space for new forms of beauty and meaning to emerge. As you lie here in the quiet of this moment, feeling your breathing slow and your body relax into sleep, you can reflect on your place within this vast temporal landscape. Your lifetime spans roughly 70 to 80 years if you're fortunate, a duration that feels significant to you because it encompasses all of your experience, all of your relationships, all of your growth and learning and love. But set against the cosmic timeline, a human lifetime is like a single heartbeat in a century, a brief pulse of consciousness in the vast flow of time. This comparison might initially seem to diminish the importance of human life, to make our struggles and achievements appear insignificant against the backdrop of cosmic evolution. But there's another way to see it, one that I find more truthful and more comforting. The very briefness of consciousness makes it precious beyond measure. In a universe trending toward cold equilibrium, in a cosmos where most matter exists as simple atoms drifting in near-empty space, the temporary emergence of complexity, awareness, and beauty is extraordinary. Consider what had to happen for you to be here, now, thinking these thoughts. The universe had to expand for billions of years, cooling and structuring itself through gravity's patient work. Stars had to form and burn and die, forging heavy elements and scattering them into space. Our solar system had to condense from an enriched cloud of gas and dust. Earth had to cool and develop oceans and atmosphere. Life had to emerge and evolve for billions of years through countless generations, surviving mass extinctions, adapting to changing conditions, gradually becoming more complex. Your ancestors had to survive and reproduce through millions of years of evolutionary history, through ice ages and droughts, predators and diseases, social upheavals and personal struggles. The chain of events and circumstances that led to your existence stretches back to the Big Bang itself, and the probability of any particular conscious being existing is so infinitesimally small that it approaches zero. Yet here you are, a temporary arrangement of matter and energy that has somehow become aware of its place in the cosmic story. You are the universe looking at itself, thinking about itself, marveling at its own existence. In you, the cosmos achieves a form of self-knowledge that, as far as we know, is rare and precious beyond any earthly treasure. This perspective can transform how we understand the meaning and purpose of human life. We don't need to be permanent to be significant. We don't need to be large to be important. A star burns for billions of years, but it doesn't know that it burns. A galaxy contains hundreds of billions of stars, but it has no awareness of its own majesty. You burn for only decades, but you can know the warmth of sunlight on your skin, the beauty of music, the joy of understanding something new about the world. You are small by cosmic standards, but you can hold the entire universe in your thoughts, can feel moved by its beauty, can find meaning in your connections with other conscious beings. The universe's timeline also offers us a unique form of comfort about death and impermanence. Everything that exists is temporary in its current form, but nothing is truly lost. The atoms that make up your body will continue their journey through the cosmos long after your consciousness has faded. The carbon in your cells will become part of new organic molecules. The calcium in your bones will join new structures. The iron in your blood will flow in new rivers, terrestrial or cosmic. You are not permanent, but you are part of something that is, part of an ongoing story that stretches from the Big Bang to the heat death of the universe. And the influence you have on the world, the love you give and receive, the knowledge you create and share, the beauty you appreciate and create, these ripple outward through the network of consciousness in ways that persist beyond your individual existence. Every act of kindness influences another person who influences others in turn. Every moment of understanding adds to the sum of human knowledge. Every experience of beauty, even if shared with no one, is a victory for consciousness against entropy, a brief flowering of meaning in the cosmic night. In the deepest sense, nothing you experience is ever truly lost, because it becomes part of the universe's growing capacity for self-awareness. Through you, the cosmos experiences wonder, love, sorrow, joy, and the profound satisfaction of understanding. Your consciousness is not separate from the universe, but is one of its most remarkable achievements, a way for matter and energy to know themselves, to appreciate their own beauty, to mourn their own transience. As we approach the end of our journey through cosmic time, it's worth reflecting on what this vast timeline means for how we live our daily lives. Knowing that we exist in a narrow window between the universe's birth and its eventual heat death, in the brief era when stars shine and planets orbit and life is possible, can infuse ordinary moments with extraordinary significance. The warmth of sunlight streaming through a window represents fusion reactions in our star's core, nuclear fire that has burned steadily for billions of years and will continue burning for billions more. The air you breathe contains oxygen created in the final moments of massive stars, released into space by supernova explosions that briefly outshone entire galaxies. The people you love are fellow travelers in this cosmic story, temporary arrangements of star-forged atoms that have somehow learned to care for one another, to communicate across the void of individual consciousness, to create meaning together in the brief span of time available to them. Every relationship is a miracle of connection across the fundamental loneliness of being individual conscious entities in a vast universe. Every moment of understanding between minds is a victory against entropy, a creation of order and meaning in a cosmos that tends toward cold equilibrium. The beauty we find in art, music, literature, and nature represents consciousness discovering and creating meaning in patterns of matter and energy. When you hear a piece of music that moves you to tears, you are experiencing the universe's own appreciation of mathematical relationships made audible, harmony, and rhythm that resonate with the same physical laws that govern the orbits of planets and the oscillations of atoms. When you read a poem that captures something essential about human experience, you are witnessing consciousness using patterns of ink and paper, of sound and meaning, to share the inner experience of being aware in a vast cosmos. Science itself, including our understanding of cosmic evolution, represents consciousness turning its attention to understanding its own origins and context. Through astronomy and physics, chemistry and biology, the universe studies itself, traces its own history, predicts its own future. The fact that matter and energy, given enough time and the right conditions, can organize themselves into structures capable of science and poetry, love and mathematics, is perhaps the most remarkable fact we know about reality. As you prepare for sleep, let yourself feel held and supported by this vast cosmic context. You are not adrift in an uncaring universe, but part of its deepest nature, an expression of its creativity and complexity. The same physical laws that govern the formation of galaxies govern the processes in your brain that generate thoughts and dreams. The same quantum mechanics that describes the behavior of particles in the Big Bang describes the chemical reactions that power your metabolism. You are not separate from the cosmos, but continuous with it, woven into its fabric, inseparable from its ongoing evolution. The darkness outside your window is not empty, but filled with distant suns, many of them surrounded by planets that might host their own forms of life and consciousness. The night sky is a reminder that you live in a universe abundantly creative, filled with possibility, pregnant with potential. Even as you sleep, stars are being born in stellar nurseries scattered across the galaxy. New elements are being forged in stellar cores. Planets are forming around young stars. Perhaps somewhere among those distant worlds, other conscious beings are looking up at their night sky and contemplating their place in the cosmic story, feeling the same wonder and connection that you feel now. The cosmic timeline we've traced together, from the Big Bang to the heat death, is not just an abstract scientific narrative, but the story of your own origins and destiny. You began in that initial expansion of space and time, when your constituent particles first came into existence. You took shape through billions of years of cosmic evolution, stellar nucleosynthesis, and planetary formation. You emerged through billions of years of biological evolution, the gradual development of complexity from the first simple cells to the intricate neural networks that generate your consciousness. And you will continue to be part of the cosmic story even after your individual awareness fades. The atoms you're made of will continue their journey, perhaps becoming part of future life forms, perhaps drifting in space for billions of years before being incorporated into new stars and planets. The influence you've had on the world, the love you've given and received, the beauty you've created and appreciated will ripple forward through the networks of consciousness and culture, adding to the universe's growing capacity for self-understanding and appreciation. This is not a story with a sad ending, despite the eventual heat death that awaits the cosmos in the unimaginably distant future. It's a story of magnificent creativity, of matter and energy discovering increasingly complex and beautiful ways to organize themselves, of the universe developing the capacity to know and appreciate itself through conscious beings like you. The ending, when it comes after trillions upon trillions of years, will be peaceful rather than violent, a gradual fade rather than a catastrophic collapse, like a gentle sunset after an incredibly long and eventful day. In the context of this cosmic timeline, your life takes on a special significance. You exist during the universe's most creative and interesting phase, when stars shine brightly and planets abound, when complexity can flourish and consciousness can emerge. You are part of the cosmic story's most remarkable chapter, when the universe becomes self-aware through beings like you. Future observers, if any exist in the far distant eras of stellar remnants and black holes, might look back on our current epoch as the golden age of cosmic evolution, when beauty and consciousness bloomed like flowers in the brief spring of cosmic time. As sleep begins to claim you, let these thoughts settle gently in your mind like snow falling on a peaceful landscape. You are ancient, made of elements forged in stars that died before the Earth existed. You are temporary, a brief arrangement of matter and energy that will eventually return to the cosmic flow. You are tiny compared to galaxies and eons, yet vast in your capacity for awareness and wonder. You are ordinary, one conscious being among many, yet extraordinary in your ability to contemplate the universe and find it beautiful. The cosmic timeline stretches out around you in both directions, from the Big Bang that created the raw materials of your existence to the distant future when the last black holes will evaporate into radiation. You occupy a precious moment in this timeline, a brief window when the universe is perfectly arranged for complexity and consciousness to thrive. The stars shining outside your window are beacons of nuclear fire that have burned for billions of years, and many will continue burning for billions more. The darkness between them is not empty but pregnant with possibility, filled with invisible dark matter that provides the scaffolding for cosmic structure. Tomorrow, when you wake, the cosmic story will have advanced by one more day, an infinitesimal step forward in a journey that spans trillions of years. Stars will have converted a little more hydrogen to helium. The universe will have expanded slightly more. New photons will have begun their journey from distant galaxies, carrying messages across space that may not arrive for millions of years. And you will wake to continue your brief but significant role in this cosmic drama, carrying with you the peace that comes from knowing your place in the vast timeline of existence. Sleep well, knowing that you rest within a universe that spent billions of years preparing for your existence, that forged your atoms in stellar cores, that evolved the complex chemistry necessary for life, that somehow organized itself into patterns capable of consciousness and wonder. You are not an accident or an afterthought in the cosmic story, but one of its most remarkable achievements, a way for the universe to experience its own beauty and mystery. The edge of time is not a precipice to fear, but a shore to rest upon, knowing that your brief moment of awareness is part of an eternal story of matter and energy, learning to know themselves through conscious beings like you. Good night.